right, class, I want to tell you on one note, the actual homework, I think it was 436 through 38, I didn't get up till this morning, it was omitted, so I'm not expecting you to know that right now. I did want to tell you, those homework problems are realization by method 2. Really, it's the method I showed you. You have negative feedback in the second part, and just using a standard summer in the first part to actually get the thing. It's discussed in the book. Does everybody understand that? That's the realization method 2 in there. And the solutions are there. Take a look at it. Make sure you know how to do that. Now today what we're going to do, are there any questions by the way before stuff? Yeah.
I was checking the homework earlier and there's not a solution for 37 on there.
Aren't there there should be these PDF file boxes. If you click on them, they'll open up.
That's what I'm saying. There's only 36 and 38.
No, that's on there.
It's all the way up there.
You have to like scroll to the top.
Right.
Sorry. Sometimes they just place it where they will.
Not bad.
But they're there. Anyway, are there any questions about the other stuff I gave you, the prior problems at all? All right. Remember, this stuff's real important. You're going to see it. You're going to see it a lot, but probably in the final end, realization of something for small things, you should be able to do it fairly quickly. Like if you just had a second order polynomial in the denominator and numerator, something like that's very easy to do with op amps, where I could just tell you the values of RC, the time constant is 1 or something like that. So please make sure you understand that, all right? Now, next thing I want to do is I'm going into Fourier transforms. I'm not going to do the Fourier series first. I'm going to do Fourier transforms, and the reason is because they exactly parallel Laplace transforms, and I started in on this. Before, when we had Laplace transforms, I had x of s equal to the integral starts at 0 to infinity of x of t e to the minus st dt. That's the definition of Laplace transform. When we talk about the actual Fourier transform, hold on. The Fourier transform is omega, and it's equal to the integral from minus infinity to infinity of x of t times e to the minus j omega t dt. I just want to contrast this. Remember, S is actually equal to sigma plus j omega. Sigma is real, omega is the frequency component. Think of it as 2 pi f, where f would be in hertz. Now, when you look at that, the reason we talk about complex frequency is we can find stability information, right? If we look in the complex plane because of that. This is really something where both of these are analyzing a waveform. They're not synthesizing it. Now, the one thing, big difference is Fourier starts from minus infinity, and the other thing, it has e to the minus j omega t. There's no sigma involved. Follow me? So sigma 0. But it also means any Laplace transform you have of a signal that's only for t greater than 0, you can get the Fourier by just letting s be equal to j omega most of the time. There are a few minor exceptions that have to do with one condition. In order for this to work or to exist, this has to be true. If you take the integral of x of t dt and put the magnitude in there, from minus infinity to infinity, it has to be equal to less than infinity. It has to be finite. If it's not finite, this won't work. You can't, if this is not true, then you can't get a Fourier transform. Now, the truth of the matter is, there's a couple of things that we have x of s for instance, u of t. Isn't u of t, the integral of u of t from 0 to infinity, isn't that infinite class?
Yeah.
Right? Well, that means that you don't technically have, you can't just take s and let it be equal to j omega and get the right answer in that case. Do you follow me? There's a special thing we use to find that answer, and that's duality. But in general, anytime you have a Laplace transform for a function that has non-zero values only for t greater than or equal to 0, you can simply take that s and turn it into j omega, and you have the Fourier. Follow me on this, class? I'm going to give you a couple examples, and we'll do it. I want to go through this because I really try to build a contrast here so you'll really feel comfortable about knowing you don't have to memorize both sets of tables. They're very obvious. First, I'm going to go ahead and put the x of t here. Then I'm going to put what x of s is. And then I'm going to put what x of omega is for a standard class. And remember, this is the definition of them all. So the first one was delta t. I think I did this last time, correct, class? If you look at delta t and you just evaluate, we know what is it for a Laplace, what is it?
1.
1. Now, is delta t only valid for t equal to or greater than 0? Yes, right? Isn't that right? I mean, it exists at 0 technically, doesn't it? It goes to infinity. So in fact, I know this is going to be 1. But if I wanted to prove it, just put delta t in here. If I put delta t times this, e to the minus j omega t, well, the delta t turns on or goes to infinity at t equals 0. I evaluate the adjacent term, e to the 0, I get 1. In fact, I get 1. That's the first one. What about this? Delta of t minus tau. Now that's a time delay delta, right? Well, what is it going to be for Laplace? Most of you know. S times tau, right? That's it, because now the function turns on at tau. So you evaluate what's next to x, or next to the delta function Laplace. It's e to the minus st, and evaluate it at t equals tau. How many understand that? All right, what's it going to be over here? Just take s and let it become j omega. It's e to the minus j omega tau, isn't it? This is how easy this is. Understand, class? I'm going to do a few more. Please follow me on this. I'm trying to show you the trick. The next function, probably we've done the most with, is e to the minus at times u of t. That's a standard exponential decay. You have to know that one, right? What's the Laplace transform of that one? Everybody? Right? We know that like the back of our hand. Now, what did I say if you want? First, does it exist only, is it non-zero only for t equals 0 greater than 0? Yes, right, the time domain function. So what did I tell you? Take s and make it j omega. And in fact, we can actually do that one, but it doesn't need to be done. It's just going to be a plus j omega. Now that is the Fourier transform. We can do it here if you want to crunch the math, but you don't need to. Understand, class? It's done for us. How many understand what I'm getting at here? Please follow me on this. I'm trying to save you a lot of, I don't know, I call it panic memorization. You try to memorize a whole bunch of stuff, you don't know why you're doing it and what you'll mean. You don't need to do that. All right, that's this one. Now, one that crops up over and over again is this one. It's t times e to the minus at u of t. I'm mentioning this for a reason. Really, we get this using a property. I'm just going to mention a property right here. We know that if I have t x of t, then over here what we actually get is minus d ds of x of s if it was Laplace, correct? Do y'all remember that? Give me a show of hands. Now, we've done this one many, many times. We know over here what I'm going to get is 1 over s plus a quantity squared, correct, class? How many know that? Got to know that one. Well, if we want what the Fourier is, we simply take the s first. Does it exist in non-zero only? I mean, for the function is non-zero only for t equal to or greater than 0, right? There's no values for t equals minus 1 that are non-zero, right? So we simply take that s and replace it by j omega, and it's 1 over a plus j omega squared. And you can see the pattern. It just repeats itself. On down. There are some special functions that are a little different. These are just, what I'm populating is something that you should know, these transform pairs. The rest of them we get from properties, and I'm going to show you that, and using a very powerful property called duality that we don't have with Laplace. So now I'm going to show you a few more properties before I get to duality. Yes, sir?
Okay, so just to make sure, like, you can do all those because they're less than infinity when you integrate them?
Yeah, they're finite values. There's the area under the curve is finite. The magnitude of x of t integrated is finite. Right? You can take a look. They all are.
Okay, right.
And for now, just leave it at that.
Okay, but u of t would be different, right?
U of t, we don't do this. I'll show you how to do that. I'm getting there. Now, I want to make sure that there are a couple other properties that you really let sink in because they're so valuable. These are all, this is just tables, right? I'm going to go ahead and erase this and put the properties over here that are important. And we'll prove some, not all, but we'll prove some. And most of these properties, matter of fact, almost all these properties, with the exception of of duality, parallel, and I'll put the properties for Laplace and Fourier up here. So now these are properties. So if we have an x of t here, and we have our x of s, this is going to be the property, and we want to know what the property is for x of omega. These are all properties now. All right, so if I have x of t times e to the minus at here, right? Over here, what happens is I get x of what? S plus a. Y'all remember that? How many do? All right, we can prove that if you want, but it's not hard to. Over here, you're going to get x of a plus j omega. Now, instead of s, you put a j omega in there. Understand, class? How many do right here? I'm going to show you some tricks. Next, if I have x of t times, I'm going to go cosine of omega naught t first. All right, before I said it would be what? Over here, I hope I have enough room to do this. It would be 1/2 times x of s, right? Plus j omega naught plus x of s minus j omega naught. Do y'all remember that, class? I'm sorry, it's crampy. But y'all follow me? How many remember that? Show of hands. Y'all remember this? This is what? This is a modulation property, right? I said it's very important. Well, when in the Fourier domain, it's even easier because you don't have the argument s plus j. What you get is this, simply 1/2. This is in the Fourier. And then it's going to be x, the actual transform of the function x of t, of omega plus omega naught plus x of omega minus omega naught. This is a very powerful theorem. It's modulation. Really, it's AM modulation. That's with the cosine. Now, with the sine. By the way, this a could be j omega right here. Follow me on this, class? And you can actually use Euler's identity for cosine and literally prove it just by using this concept right here. So now if I have x of t times the sine of omega naught t, now I get that j term. And here I would get what? J over 2, and it would be x of s plus j omega naught minus x of s minus j omega naught, right? Y'all remember that from before class? Show of hands, how many do? It's very, very straightforward. That was the sine, right? You had a j over 2, and instead of adding, you subtracted the values of once they're skewed by omega naught. Well, over here, you're going to have the j over 2, and it's going to be x of omega plus omega naught minus x of omega minus omega naught. So it's almost the same as this one, only there's a j here, and instead of additive, they're subtracting. By the way, this is an even function, and this is an odd function, generally. I'll get to that in a second. You'll see that this has to do a lot with communication theory later in your, as you get, let's see, in the next course you get is random signals and systems, then you get COM, and COM you'll appreciate a lot of this more. Now, I want to just take a moment and focus on what these things actually look like in the frequency domain and do one for you, okay? So I'm going to erase this so I can actually show some contrast here. All right, I'm going to take a function, and here it is. I'm going to say I have e to the minus, say, 2t times cosine of 10t of t. And that's my function x of t. And now I want the Fourier transform of that. Follow me, class? This is a very routine question. First, if you ask for the Laplace transform of that, you would probably go for e to the minus 2t u of t first, and then say if I have that transform, right, I have x of t goes to x of s. Then if I have the e to the minus 2t u of t times the cosine, I can just take the 1/2 and take the original x of the function where I just had the, for the u of t, or e to the minus 2t u of t, and add the skew to it. But if we do it in the Fourier, what this will become, it's very obvious. You agree that a is 2, right? Omega naught is 10. Maybe if I put it down, a here would be 2. Omega naught here would be 10. Agree, class? Now just write it out what it is. That means it's going to be 1/2 times, well, e to the minus 2t u of t is simply going to go to 1/2 plus j omega. Correct, class? Everybody see that? Isn't that right? So that's my x of t, you can think of it, times cosine. So now I'm going to take this x of t, you might say the x of omega, and put this, or add the omega naught to it. So now it's going to be 1/2 plus j of omega plus omega naught is 10 plus 10. Then it's plus 1/2 plus j of omega minus 10. Does everybody follow me on this? Give me a show of hands if you do. That is the literal Fourier transform of this. And what I did is first, I called this my new x of t, right? And I got the transform pair of that. And then it's multiplied by the cosine. So I know the e to the minus 2t u of t goes to 1/2 plus j omega, right? And then I simply do this. Wherever the omega is, I add omega naught to it. And then I subtract omega naught to it and put a 1/2 in front. How many see this? Now, the important thing is you see what this looks like in the frequency domain. This is very important. So if I graph this, and I'm just going to graph the magnitude, not phase. If this is omega, and I graph the magnitude, this is my transform of the entire thing. That is my x of omega. When I take a look at the magnitude of x of omega, this is like, you can liken it to, the square of it is actually the power, but this is really the signature in the spectral domain of, you could think of the voltage or electric field, all right, in the frequency domain, what it looks like. So you come up, the way you do this is you go down to minus 10 and plus 10. Those are the center points. Now, can you all see how this function 1/2 plus j omega plus 10 right here will have a maximum value when omega is minus 10, right? Minus 10 plus 10 is 0, so it's 1/2 or 1/2. Correct, class? Times the 1/2 is going to be 1/4. Agreed, class? So basically, this thing's going to have a height here of about 1/4, and it'll look like this. It'll be similar to a bell curve. All right? Narrower, it's an exaggerated thing. It'll be a lot narrower than what I'm showing you. Now over here, you're going to get the same thing. The height of this will be 1/4, and it'll basically be like this. It's an exaggeration. I've spread it more. It's actually a much narrower band there. Now, the square of that is proportional to the power density. The reason I'm telling you this is when you actually really start working with equipment, you're going to work with things called spectrum analyzers. Has anybody ever heard of this? A spectrum analyzer will usually put an antenna out there, or you can feed a signal right into it. And what it'll do is display it's usually the power density, power spectral density, or voltage. You could say that voltage versus hertz. And you'll get something like this. And what you always look for is you look for where these peaks are. That tells you the carrier frequency involved. Understand, class? The other thing, the spread on this, and I'm not going to spend much time on it, the 3 dB spread where the actual power goes to 1/2, the bandwidth, that's the bandwidth of the signal, basically. And I'm just giving some insight in your later classes. How many have heard of bandwidth? Right? And you know what carrier frequency is, and that's what you'd literally see if you were looking on a spectral analyzer, that type of signature, or the square of this, where they actually take the magnitude squared. One other thing too, I didn't say this, but usually they don't plot omega, they plot f. So you divide omega by 2 pi in its versus frequency, because that's a common measuring tool. We talk about things in hertz, not in radians per second, usually when we are doing any kind of analysis. Anyway, that's important to know. Now, believe it or not, the magnitude of that waveform would be the same as if this was a sine omega naught t. Exact same signature in magnitude. The difference is the phase. And in communications, you'll see the importance of phase later, but not right now. Just for now, understand that's what the signature looks like. Got me, class? This is important. Now, after this, x of t, sine of omega naught t, modulation. I'm going to mention these. I'm not going to prove this one. If you want me to, see me in my office. I'll be happy to prove it. Remember, what happens if we convolve two signals, x of t convolved with h of t? What do we get?
That's just excess.
Multiply the x of s times h of s, right? We get rid of the need for convolution. So this is really going to be x of s times h of s. It's the same way for the Fourier transform. It would be x of omega times h of omega. So that would be the same thing. Exact same thing for convolution. And thank God.
Not j omega?
Couldn't hear you?
It's not j omega?
Well, the j is included in the functional form. It's omega is the variable.
Alright.
If that book puts a j in there,
I was just wondering.
some books do, and it always irritated me. It's a function of omega, all right? The j is there to show phase in the actual definition of the function. All right, now the next couple of properties, I mentioned the derivative, multiplying by time. I'm going to say this one. The one with integration, I got to show you how to get this. Now with, I'm going to show you duality. But first I'm going to show you what it says. It says that if, I got to do this right. Well, yeah, I'll just show you this. If you integrate x of t dt, and you go from minus infinity to t. Now, this is at minus infinity starting, not at 0. Remember when we did the integral property with Laplace, it started at 0, class? And we're doing this, and I got to put the t prime here, and we want to know the transform of that. You're going to get something. Remember when we had the integration property, if we had the integral of x of t dt from 0 to t, and we wanted to transform, it was 1 over s times x of s. How many remember that? Derivatives bring an s in front, integrations bring a 1 over s, right? Well, over here it gets a little different. Now instead of an s, you have 1 over j omega. That makes sense, times x of omega. If you have your book, you're going to see this. And that is absolutely true everywhere except when omega is 0. Because when omega is 0, something weird happens. Now you're going to get something called pi, which is just pi. Then it's going to be times delta of omega. And then it's going to be x of 0, where this x of 0 here is actually the integral from minus infinity to infinity of x of t dt. Now I'm going to explain something to you. This should make sense. That's like 1 over s, x of s. That's true everywhere but at 0. But at 0, there's something odd that happens. Here, you're going to have something where it's really an impulse. It's going to be, it's more or less an impulsive function where all the DC energy is at that point. I'm going to have to show you how I can explain this better. Just hand waving won't do it. So I'm going to use duality now. And I have to do this. I'm going to have to erase that to show you what I'm up to. I'm trying to do this in a way, the book doesn't even really, in my opinion, he doesn't even take a shot at explaining this. He just kind of states it and moves on. And it's important that you see this as engineers. You're going to have to understand why this works and what the real power is. All right, now, I gotta complete one thing I did. Remember how when we had Laplace transforms, you don't need to write this, just listen to me. With Laplace transforms, the analysis was x of s was equal to the integral from 0 to infinity of x of t e to the minus st dt. That's analysis. That's the one we use all the time, right? We never did an inverse Laplace transform to get x of t. But if we wanted to, x of t technically is equal to 1 over 2 pi j times the integral from minus infinity to infinity of x of s times e to the st ds. This would get it, believe it or not. This is synthesis, or the inverse. Now, we don't do that. We use partial fractions always, don't we, class? Because, first of all, that can be a wicked integral. And there's no need to cause more pain than necessary. So we omit that. However, when we deal with Fourier transforms, this little guy here is going to help us a lot. We're going to be able to really leverage some stuff, and I'm going to show you why. So with Fourier transforms, x of omega, this is going to be analysis, is equal to the integral from minus infinity to infinity of x of t e to the minus j omega t dt, and x of t. Now, this is the synthesis. In radar, we do this, by the way. And I'll get to some of this later. This is actual synthesis. It's 1 over 2 pi, there's no j there, times the integral from minus infinity to infinity of capital X of omega e to the plus j omega t d omega. I need to mention something. This is analysis. This is the standard way we do it. I mean, this is analysis too over here. We're analyzing a signal. This is technically synthesis. We never do that. But over here, we're going to do it. And we're going to do it in a very clever way, though. And I'll show you how in a second. Now, if you look at these two for a second, here, let me give myself some room and make sure I really hit this hard so you can see it.
Wait, what is that? X?
I'm sorry, what?
What is that? M?
This is x of omega. It's this.
Oh, okay. Oh, okay.
All right. This is analyzing the signal, so you get an x of omega. This is synthesizing. Normally, what we say is if we want a certain filter property, we put that filter property here. We know how we want to make the signal. We want to know what the filter does, and this would be the actual, it would be the impulse response that would come out of the filter if you put an impulse in. But it's really called synthesizing a waveform. Don't worry about that right now. It'll make more sense in a bit. Now, if you look at these two, the one thing you have to understand about engineering and about mathematics right here, really t and omega, we interpret t as time and we interpret omega as frequency. But they're just dummy variables. They can mean nothing or can mean everything. Follow me? In the mathematical world, they don't have to have any interpreted meaning. Now when I look at this, I'm going to do something. If I go ahead and I take this relationship, and then I'll take the omega and make it t, and I'll take t and make it minus omega. Now just listen, before you start writing, here's what I'm going to do. Remember, these are dummy variables. So now I'm going to do a switcheroo. I'm going to say this omega is now going to be t, and that t is going to be minus omega. And that should bother you a little bit. You'll see why in a second. So when I do that, here's what I get. I get x, capital X, by the way, that's going to be the transform, capital X of t is equal to, and then I get this integral from minus infinity to infinity of x of t, which is x of minus omega, and then it's still going to be e to the, now not minus j omega t, but plus j omega t, and not dt d omega. Are you with me, class? You're not going to like it. This is duality. I just literally did a switcheroo with variables. I can define variables. I could just as well say w is x and t would be something like k. Doesn't matter what variables I use here. Understand? But here's what reason I chose those. Now when I look at this, I notice that this has the exact same form as this. Just take a look at that. There's an e to the j omega t. There's some function of omega it's multiplied by, and the integration is over omega from minus infinity to plus infinity, right? How many see this? Now, what this really is, if you look at it, that is the synthesis. That's the inverse. Take a look at this. This is the inverse Fourier transform. This is the Fourier transforms. That's the inverse, except what? Except here, I don't have the 1 over 2 pi. Do I, class? Right? So now I take a look at this and I say, well, when I take a look at this, let me just explain this, that really what I'm going to get here is there will be a 2 pi that will pop out, and I'm going to just show you what I'm doing here. This is called duality. I'll spend a little more time with this, but this is what really happens. Let's assume you have the relationship x of t goes to capital X of omega. All right? We're going to assume I know an x of t and I know an x of omega. This is capital X of omega. Please write this down. This is so important. He does not underscore this enough. Now that is a physical form of a function. X of t, if it's delta t, and I'm going to give you an example, if it's delta t here, then this is 1, isn't it, class? Right? Now what duality says, if I take the physical form, the functional form of this, and instead of omega I put a t, so I put capital X of t here. Say if this is 1, well, replacing w by or omega by t doesn't change. It would just be 1 over here, wouldn't it, class? How many see that? Then over here, you take the functional form of x of t, the delta t, but now you multiply it by 2 pi, and instead of t, you put minus omega. Actually, let me do it this way. It would be 2 pi times x of minus omega. Now, this concept requires some concentration. I put the delta t1 here for a reason. Now, if we wanted to use duality, suppose I wanted to see what happens in the time domain if there's 1. So when I take this value down here, right? Technically, I'm supposed to take omega and turn it into t, but that's not a function of omega, so it's just 1. Got me on this? Now, when you talk about 1 in the time domain, isn't that the DC value of something? Right? 1 all the time is just like a DC battery of 1 volt, isn't it? There's never a time-varying change. Well, duality says that in the frequency domain, the signature looks like 2 pi, and I take this functional form, which is delta t, but now I replace the t with a minus omega. Got that, class? So now I have delta of minus omega. Using duality, I'm going to do several more of these so you can appreciate this. Now listen to me carefully. First, does it make sense? If you have DC battery, never changes versus frequency, where do you expect all the energy to be in the spectral domain? Omega equals?
0.
0, all of the energy, right? And it sure is. All of the energy is there. It's this. I'll get to the actual, it's a couple of theorems that we're talking about, Parsifal's theorem, about how to actually calculate the energy in a signal and time and frequency. But now just appreciate that. Understand, class? That's it. But there's that 2 pi weight. Now we get to u of t. And I'll show you, let me do another duality problem, suppose, because you're gonna probably really be scratching your head on this one. I know that, because it's not an easy concept. I'll give you one more. And I'll put down duality again. Make sure you write this down. It's the most important property, in my opinion, with Fourier transforms. This is duality. If you know an x of t goes to some capital X of omega, I know this relationship. Then if I have this functional form, whatever it is, could be a sine, cosine, exponential, whatever it is, if I come over here and take capital X and I replace omega with t, and then I take this functional form, and I multiply it by 2 pi, but not x of t, x of minus omega, now I have this transformed pair as well, without ever doing any further integrations. You understand? That's duality in a nutshell. So I did the one where I said, I know if I had delta of t, I got 1 in the frequency domain, right? So now when I want to know the value of dc, I come over here, and I put 1 down here, and over here, now it gives me 2 pi times delta of minus omega. I have a question for you. When does delta of minus omega turn on and go to infinity? Omega is 0. Do you think that minus sign makes one bit of difference?
No.
Matter of fact, for any even function, you don't need that minus. You can just make that plus. Now I have the relationship. Now listen carefully. The reason we can't do u of t directly, the Fourier transform on it, take a look at this. Suppose I wanted the integral, remember the Fourier transform of u of t would be the integral from 0 to infinity, right, of 1, right, because it's just 1 from 0 to infinity, times e to the minus j omega t dt. Well, what's that going to be? That's going to be what? Minus 1 over j omega, right? Times e to the minus j omega t, evaluated from 0 to infinity, right? Isn't that right? Well, when you evaluate this, you have to have e to the minus j infinity. What is e to the minus j infinity? It's undefined. It's something that I don't know. Neither do. This is one of the things that mathematicians love, this kind of stuff. You can't get at it this way. Understand? You can't get at it a direct way. But through duality, you can get at it. And in fact, what happens is if you integrate just 1, I mean, this is for all infinity, you get this, right? Well, what is 1? I'm going to just tell you this. Isn't 1 u of t plus u of minus t? I mean, I can do it a different way if you don't like that. There's several different ways. I'm just making this hand-waving argument. Y'all give me that? All right, now I want you to think about this. If this plus this goes to that, what do you think this goes to? That's right. And what happens is this. This isn't exactly true. I'm sort of just kidding with you about this one, but what happens is that you can see that what you have is a way of getting the value of 1, right? Do you agree with that? Now, what is u of t? Isn't u of t, you could do this a couple different ways. He chooses to do he has something where he has a function called a sigma function, all right, in there. I'm not going to play with this anymore. I've got to take care of 2 things. But he calls, do you know what a sigma function is, SGN? In there, do you all see that in his book? He's got SGN function defined. He does it, he uses this functional form. I'm not worried about this right now. I don't want to start going that route. What I want to tell you is you can get u of t then very easily. U of t itself, knowing duality, will be simply equal to 1 over j omega as such. And then it's going to be plus pi times delta of omega. And you'll have that. Do you all see that in the book for u of t, class? Anybody have your book here? Can you see the transform of u of t? This is like 1 over s. You remember with Fourier transforms, or Laplace, it's just 1 over s? What this is, this accounts for all the actual spectral power, energy, amount of the signal at DC. That's what this is. Do you see it? Anybody see it? How many see this right here? It's there. Look, what table?
It's on page 228.
All right, take a look there. Page 228. I just want you to know that this is u of t. Now, I got more to do. So now, last thing I have to do, actually I got 2 things to do. Remember before I said there's certain classes of function that are symmetric about t equals 0. The pulse function was the first. Please watch this. So the first function is when we have a pulse of tau of t, he refers it to a rect of t over tau, that function looks like this. If this is t, this is minus tau over 2, this is tau over 2, this is the pulse function of tau of t, has a height of 1. Are you with me? Now, if we want the Fourier transform of that, we can do this directly. So I can say, if I want the Fourier transform of that, I can say that it would be the Fourier transform of this would be equal to the integral. Remember, the Fourier transform is the integral from minus infinity to plus infinity, but this only has non-zero values from minus tau over 2 to tau over 2, correct? So I go from minus tau over 2 to tau over 2. Its magnitude is 1 times e to the minus j omega t dt. Now we go ahead and do the integration on this one. And this integral becomes 1 over minus j omega. And then it's going to be times e to the minus j omega t, evaluated from minus tau over 2 to tau over 2. I've just put in the limits. Now what I can do, since this is a minus sign here, I can switch the limits and evaluate it. And I get this. Right? I get e to the j omega tau over 2 minus e to the minus j omega tau over 2 over j omega. Do you all agree with me there? This is just getting the Fourier transform. How many do? Are you with me? It's straightforward integration. There's nothing tricky about this. So I'm down to this point. Now, what do you suppose this is? What's a good way to make a nice compact statement of what that is?
Sine.
It's the sine, isn't it? It only has a 2j in front of it, doesn't it, class? Because I know that sine of theta is actually equal to e to the j theta minus e to the minus j theta over 2j, don't I? So if I multiply by both sides by 2j, I get e to the j theta minus e to the j theta. And the theta here is omega tau over 2, correct, class? So that means this is really going to be equal to 2j times the sine of omega tau over 2 over j omega. I'm going to stop for 1 second. You can see the only thing I'm doing is what? I'm crafting it in a way to try to get compact. Sine is something you're familiar with. 1 over omega is something you're. Does everybody see the j's cancel, class? Show of hands here. How many do? Sure they do. So if the j's cancel here, now I have this. Now, here's my goal. I want to get this argument, omega tau over 2, down here. So can I take the 2 here and divide top and bottom by a half? And now I have this, right? You agree with me there, class? And now I'm going to multiply top and bottom by tau, and there's a reason I'm doing that. Does anybody know the reason why I'm doing that? Why would I want this to be equal to that? Anyone? I know people know this. There's a function called sinc. Sinc, right? What is the definition of a sinc function? S-I-N-C. This is one definition. Sinc of x is sine of x over x. It's very, very common in engineering. There's another form of this, as sinc of x is sine of pi x over pi x. And they're both fundamentally the same. But this is the functional form that we use in this book for sine, for the sinc, S-I-N-C of x. How many have heard of sinc? You should have in your physics courses seen this. All right. Why? Now look at this carefully. Do you see how I have sine over sine of omega tau over 2 over omega tau over 2? That's the sinc of that argument. So this is really equal to tau times the sinc of omega tau over 2. And in fact, that's what the transform of this is. You can say the transform of a pulse is tau times the sinc of omega tau over 2. And write that down. And I'm going to show you what it looks like, because it's very important you understand this one. There's a triangle function too that you have to know, but this one's very important. So if I look at that, and I see that this is the time domain waveform. It looks like a little pulse of a certain width. It goes to that in the frequency domain. Here's what this looks like. If this is omega here, and I looked at that sinc function, the tau times the sinc of, I'm just going to put it, tell you what, let me just show you sinc x here. Keep the variable versus x, not omega. What that'll do is have a height of 1. This is SINC, by the way. Make it larger. SINC of x. It starts out with a magnitude of 1 at pi, and at minus pi, it goes to 0. Then it goes negative, and it starts falling. The amplitude, the magnitude of that starts falling is 1 over omega. And then at minus pi, 2 pi, pardon me, or plus 2 pi, it goes back to 0, and it does this, just meanders on down. Same way with this one. The zeros are always at the argument here, either pi, 2 pi, 3 pi, and such, because the sine of pi is 0, sine of 2 pi is 0, and so forth. Do you follow me, class? Now, if you just take the magnitude of the sinc function, which is usually done, when you take the magnitude of the sinc function, then you get this, basically. And it's asymptotically going to 0. Do you all see this, class? This is very, very important. You're going to see this function all around. I teach radar, EMC. You'll see it in controls. You'll see it in random. You'll see it everywhere. And it's very important that you understand it. Now, that is the transform of this function. And what do you see happening? The narrower this gets, right? If you look at this function, you see you have omega tau over 2, right? The narrower this waveform gets here, the broader this first bulge, or really it's the first, honestly, you could say the main beam of that thing gets wider and wider. Narrower in the time domain, wider spectrum in the frequency. This is real important. And in the limit, as this thing went to be an impulse, you would have just a constant value all through the frequency domain, same magnitude. Remember, a delta t goes to 1, right? What does that mean? It means the spectral energy or spectral signature has the same magnitude at every frequency. A delta function is extremely wide band. And the broader this thing gets, the closer to DC all the energy is. Remember that. That's a standard thing that you need to think about as engineers. I'll tell you what I'm going to do. I'm not going to do it right now. If that's a pulse, the next function where it's interesting we need to do is a triangle function. 1 minus pi, or minus tau over 2, and then tau over 2. And I'm going to do that next time. I'm going to give you some homework. The actual, tell you what I'm going to do first. Instead of giving you one where you have to do a synthesis with realization 2, what I'll do is give you something on basic Fourier transform stuff. So you've got the Laplace under your belt for a quiz on Friday, okay? Basic Fourier, and I'll give you some problems. Right, but don't forget that synthesis, because that's something you're going to get.